here, Owen, Jeremy,
Take a computer science maybe and put it on that.
Colin,
It's like a time. Did one show average money. It's listed at 28. I have like a whole dealership that was marked.
Jack, and Zach.
I mean, it was like my first time calling him. So I really just shook the guy down.
Jeremy. Go. So these are the exams. Generally, the class did quite well. Answers were on target and accurate for the most part. There was, some points you get a little bit off here or there, or just kind of misunderstand, one section, but that doesn't affect that much. But 10 of the students were in the 90s to 100. 11 in the 80s, upper 80s to lower 80s, and a couple in the 70s. So it overall, that everybody in the class is at a point with this, that they either have very good scores now, or that a little bit was missed on parts of things, but with a little bit of studying and work, it would be possible to raise those through continuing to do the homework, the second exam and the final, and a project. So this is just kind of one piece of the grade. But generally, if you have grades you're happy with, that keep up the good work, keep up with the homework, keep asking questions. If you would like to raise the grades, solutions are posted, so you can compare to the solutions that are online and see what they say, see how things were answered a little bit differently, and some of the details. But then as the as homework continue, the next exam approaches, if you feel spending a little more time coming to office hours or asking questions, or a little more time reviewing and studying as going along, there's a potential you could raise the grades. So in general, it was quite good on answering many of the questions. But any questions or comments or so check out the solutions. Save these and let me know if you have questions about things. This is homework 5 had been available outside my door, and a few people came by and got homework, but let me just go and give these back quickly since you're all here. So, Austin. Katie. Joe and Devin. Jen. Colin. Matt. There we go. Gordon. Jack. Zach. And then Alex. So I'd like to give back the tape after the term is done. I'm sitting in my office, so it doesn't do me much good. So, the last time we did the new material, we were looking at continuous distributions, which means continuous probability distribution. Right? This so you can see the screen. So I will post another homework, a homework 6 will be posted. It'll either be later today or maybe tomorrow morning, but I'll make it whether there be a few problems we should do for Tuesday, or it should be made for Thursday and encompass a little bit more. But anyway, I'll send out an announcement about that. So we're looking at continuous probability distribution. distributions. And for those, we specified a probability function. A f of x was a probability density function. PDF. And it was over some range, generally, of x, any kind of thing here, density. And that gave some information about the likely values of x that would happen in an interval. The higher that is in different places, that's where you're more likely to have observations in terms of the x values. Total area under this thing is 1. We also looked at a cumulative distribution function, the probability that x is less than or equal to a particular value. And in a continuous case, that's an interval of the density of the PDF. I'll put a little placeholder in here, maybe y. And this is called the cumulative distribution function, or CDF. And so it's a function that, as x goes along, accumulates probability that it's always increasing for continuous ones, and it goes up, it asymptotes at 1, because as x gets bigger, you get the entire area under that PDF. In there between 0 and 1, and so this is the graph of this capital F of x. And a couple of ways that that cumulative was used is if you wanted the probability, I'll put this on that, I'll get it in here, say the probability that x is between two points, well, you could either look at the PDF, the density, and integrate from A to B of the density. So under the first curve, just between 2 points, the area under the curve, whatever that function is. Or if you already have the CDF, right, you can do the probability you're less than B and then subtract out that you're less than A. So this is equivalent to the CDF at B minus the CDF at A. So you can get the probability you're in different intervals depending on that. So looking at these two pictures that are over here on the side, and I can go back. If we had 2 points here, A and B, right, the area, the probability you're in there is the area under the curve. But in this case, if it kind of maps down here to A and B, the cumulative, and here's the probability that A is less than or equal to B, less than or equal to, X in the middle, B. Like this, they have the probability between A and B, and then it's the difference between those two cumulatives. Right? Either way you look at it, you can get the probability. But anyway, that was a little review. We'll do a specific example today to look at these things. And maybe it's time to switch to looking at that. Let's do the uniform first, just as a quick example. So a uniform random variable is one that just goes between 0 and 1. The density here is just flat. Uniform between there. Outside of 0 and 1, the density is 0. So our f of x density function is simply 1. If we're in 1, we can either include the endpoints of 0 or 1 or not, right? Because it's continuous, there's not really any area at that point. It's not going to make a real difference in our calculations. And so the cumulative distribution function is just the integral of that density. Now below 0, it's right, below 0, it's 0. And then if this is 1, after 1, we've had all of our density, so it's going to be up there. And so somewhere between 0 and 1, it's increasing between those two. Right? And it's increasing determined by, so f of x, f of y, just a placeholder, but it's constant. It's just a constant of 1. Right? The constant of 1 is just the value, just whatever you're integrating there. And then we evaluated at our two endpoints that we're interested in. So it's just x. It's just increasing. Right? It's a nice straight line here. So if we're interested, for some reason, what's the probability that 1/3 is less than, that we're going to get a random value, oops. Let's go crazy. Oops. Okay. I'll reset it. So this is less than x is less than 2/3. If we're interested in that for some reason, right, then it would say, the cumulative would say we could just take the cumulative function at 2/3 minus the cumulative function at 1/3, and because of this just linear increase, it's just 2/3 minus 1/3 or 1/3, which is not surprising at all, because it's easy to see that between a 1/3 and a 2/3. Right, and here, the area in this sliver here has to be 1/3, and so that's what we would expect the answer to be, right? But let's take just a little bit more involved example. Right? So it turns out that if U1 and U2 are two independent random variables that have a uniform density, right? That if you take their average, let's call it A, as U1 plus U2 over 2, that the resulting density for our new random variable is actually a little triangle. We're taking the average, U is between 0 and 1, U2 is between 0 and 1, and so the average also has to be between 0 and 1. But the density is going up as you are less than 1/2, and then it's going down. There's how it ends up working out. The equation for the density, now the total area has to be 1, right? And the area of a triangle is 1/2 the base times the height. Well, the base here in this triangle is 1. Right, that length is 1. 0 to 1. That interval times the height, and that has to equal 1. So in this graph, the height has to be 2, right, to make that work out. And to specify the density, well, it's 0 if our little value of v is less than 0. There's nothing going on there. Going up here, it's a straight line going up, so the equation is actually 2 times v. As it's 4 times v, sorry. So you can check, so at 1/2, make it less than or equal to, and this one less than or equal to, just to cover the whole range, it's a 2 in there. As get 1/2, the height is going to be 2, and it's that linear increase. And going down on this side, the equation of that line is actually 4 minus 4 times v. That, yeah, 4 times 1. If v is less than 1, and it's 0 if v is bigger than that. All right, so we get these two different equations that really talk about the density there. Right? So now, for this type of thing, what's the cumulative distribution function? What's the CDF? We're going to have to kind of take it in two pieces, because you can't write one equation to integrate over this entire space. Right? It's a little different if you're below, and then if you're above. So that's our density. But any questions about why this is that? As we go forward, we will start with two independent uniforms and prove that this is the density. Right now, we're just going to take this as the truth, that that's how it is. But we'll have this method called convolution, where we can figure out what it was, what it would be, what would it be if we had the average of 3 or the average of 4, and so on. This is this density. So for the cumulative distribution function, it's easier to determine probability. We have to break it up into two parts. Right? We have to do this part that is less than here. So the probability that our random number is less than or equal to some v, if it's in that integral, well, it's just the integral from that, and just that density function, that PDF applies there. So it's just an integral of this one, right? 4 over v. So v squared over 2, and 4 over 2. So that's 2 times v squared. Yeah, I guess you could put a different placeholder in here if you wanted. But it's evaluated at this thing going from 0 to v, so it's just 2v squared. So as we go from 0 to 1/2, I think this graph at 1/2, it's 1/2 times, it goes up to 1/2. The CDF is accumulating kind of like this. It's going quadratic instead of linear. As a PDF, as a density PDF, this is the f of v1. We're trying to figure this out. This is the graph of the cumulative. As you go along, you get increasing amounts of density, right? And so it's actually going up at a quadratic rate, right, as you go along. What do you think it looks like after you get past 1/2? You have the same pattern, but just inverse. It's going to have a lot of probability still accumulating for a while, but it's going to, it's going to be kind of the mirror image around there. So this one works if v is less than 1/2. At v equals 1/2, the density, the CDF, the probability that our random number is less than or equal to 1/2, is 2 times 1/2 squared, which is just 1/2. We've gone through half the probability once we get to 1/2. It's symmetric about that. So if we want the probability that it's less than or equal to v for the second half, so right here for the second half over here, we have to use the combination of these things. To be less than this, right, what do we really, we've already used that 1/2 here. And now we have to add in a little piece that is above whatever the extra bit is. Right? So we need to effectively add in, say we were interested in this value of v over here. Well, we have 1/2 that's already happened, and then we need to add in that little piece. The general equation doesn't change. We still want to go 0 up to v. of the density. And I'll put W in here as a little placeholder. Right? But because the function changes, we split it at 1/2. And then we go from 1/2 up to whatever number we're interested in. And this first part we know is 1/2. Right? And then in this second range, we have to put in our 4 minus 4W is V. That other line that's going down, the density that's appropriate for that area. That's a little bit, because of that because the change in the definition of the curve, it changes like that, right? So what does this mean? 1/2 plus, then integrating that one, 4W minus, what we think of W squared over 2, so there's a 2W squared here, evaluated from 1/2 up to V. So at V, this thing is 1/2 plus 4 times V minus 2V squared. And then at 1/2, we're subtracting all of this. I guess if there's a minus, 1/2 goes away, minus 1/2. This thing at, when W's 1/2 is 2, and then another minus, and then it's minus 1/2. Right? So what do we get when we put all of this stuff together? I've done this right. The 1/2s are gone. There's like this 4V minus 2V squared minus 3/2. If I've done everything right. V 4W. Okay, 4W minus 2W squared. And at V, what is that, 1/2? I don't need this extra 1/2. Right? That's what my problem is. This 1/2 was out front of everything. In the integral, there's no 1/2. So I did it too many times. Okay. So the 1/2s cancel, and it's 4V minus V, and then minus 2. So this is the other cumulative. When V is 1, where we know all the density in, it's 4 minus 2 minus 2, and it's back to 2. 2. Oh, this would be minus 1. It's good to check. Right, so at 1, right, because minus minus is plus. So there's 1, and then there's a minus 2, so there's just a minus 1. Right? So when V is 1, and we've used up all our probability, this thing has to be 1. So it's 4 minus 2 minus 1 is 1. So that's the answer. So that picture is a quadratic, but it's going up here to 1 and going off this way. And then we know it would continue at 1 after that because we don't have any other probability. So that's the cumulative. It's a little bit funnier because of that split. But any questions about? So for this one, right, what's the probability that this one is between 1/3 and 2/3? Well, at the top, we're going to do the density at 2/3 and the density at 1/3, cumulative. So at the top, it was, do I have it down here? 4 times 2/3 minus 2 times 2/3 squared, 1. That's the top one. And then we use the lower one, which was just 2x squared, 2 times 1/3 squared at the lower side. And if you figure that out, you would get the answer. So 8/3 minus 8/3, right, minus 1 minus, you can't have all these minuses, right? Minus plus So 8/3, 2, 4, minus 8/3. That goes away, minus 1. This can't all be less than 0. This other one up here. Let's see, do I have it correct? Did I write down the right thing? Minus 2b squared minus that. 4. 2/3. Oh, this is not thirds, it's ninths. That would be good to do the math, right? Yeah, so. And then this one is minus 2/9. Right? So if you put everything over ninths, 3 times this is 24, minus 8, minus 9, minus 2. So it looks like it's 10, 19. It's like 5/9. Before we had 1/3. 1/3, which is the case of the uniform. Yes.
Is that for the minus 2e squared minus 1? Is that the CDF after 1/2?
Yeah. Right. This is the CDF that we use over here because 1/2 is greater than 2/3, so we use this function. On this other hand, 1/3 is less, we use that function. We use whatever's appropriate in that. So anyway, there's 5/9 chance of being in this 1/3 and 2/3, but on the uniform that was spread out more, there's less. So you can do these kind of calculations on those things. Right. 2 other things that we can do. We can look at expected value of a random variable. So if f of x is our PDF, our probability density function, then the expected value of a random variable, the continuous one, is we're going to take the values times the density. And since it's continuous, we're going to do it over all the range and integrate that. When it was discrete, we took the value times the probability and added them up over all of those. Right? But when it's continuous, that turns into an integral. And if we have any other function, like x squared, we can take the integral of whatever function we have in there. So x squared becomes the thing here, and take the density. So for a uniform, yes?
What is the squiggly x?
So this, so I guess the distinction, right, so maybe, is that I try to make a distinction between random variable right, so kind of a capital, and then the actual values that you would see.
Oh, okay. It's just,
So, and so try to make it a lowercase, or try to make it squiggle to make it a little bit different. Right? So, and then the values. So I'm not terribly consistent, but try to make them smaller, right? Just to distinguish between the random variables, kind of the theoretical process. It tells you what you're going to measure. It's going to have a range of possible values, different likelihoods of things. Whereas the x's are the actual values that you take on. So this one is big, right? And these are smaller ones, written like that. Good. So for uniform, you know, 0, 1 is the integral of the value times the density is the general formula. The uniform 0, 1 only had density between 0 and 1, so we'll restrict it to that. And the density itself was uniform, just constant along that, right? Times dx, so we get an x squared. This is actually a little bit more interesting. Right? Well, we'll do this one. So x squared over 2, evaluated x equals 0 and 1, so it's just 1/2. Right? As it's symmetric about 1/2, you would see the density, half the probability is above, half below. It's exactly reflexive about that, and so it's not as surprising it's right in the middle. A uniform that goes between 2 points, you could shift the uniform random variable to start between any 2 points. And if it's uniform between that, right, we would mean that the density function, so the values of x and the density is just uniform in between there. So you might change it if you're dealing with percentages of voting on a subject, the percentages of looking at what, to take all the school districts, what percent of children in the school districts have their immunizations or experience the flu in the year. There's a percentage. So you might change it from 0 to 1, or other things might be on a different scale. Right. So if that's it, the total area is still 1. Right? And so the area is the height times the base. The base is b minus a, this distance here, times the height. So the height here has to be 1 over b minus a for these two things to multiply to 1. So in this case, the density for this uniform is just 1 over b minus a if our values are in here and 0 otherwise. To compensate for if it's stretched out more, the height goes down to keep that area there. Right? So what's the average of this one? It's going to follow kind of the same plan here. It's not much harder than the other one. It's just a little bit more interesting because you're not just doing 0 to 1. It's going to be the density, 1 over b minus a. There's an x in here times the density. So there's a 1 over b minus a, and then x squared over 2. And we evaluate that at values of a and b. So I'll pull the 1/2 out and the 1 over b minus a. And so when it's b squared minus a squared, you pull all the other stuff out. But b squared minus a squared can be factored. So just remembering that algebra, it's b minus a times b plus a. And so we get b plus a over 2 as an average. Where is b plus a over 2? Well, that turns out to be right in here. So this is where the expected value of x equals for this one. Again, maybe that's not surprising. This is symmetric. It's equal chances on all sides. So you get some that are above that point, some below, but it kind of would balance out to be there in the middle. But that's the concept of expectation, right, that we would do. It turns out that for the uniform 0, 1, the variance of x, which is the expectation of x squared minus the expectation of x, turns out to be 112. And if it's uniform between 2 points, then the variance of x ends up being b minus a squared over 12. So nothing magical or greatly deep about 112, but that's just the number that it ends up being. So if you did the integral from 0 to 1 of x squared with a density that's the height of the times dx, it's going to get some value, and then if you subtract 1/2 squared or 1/4, it ends up being that. And then you would get this thing for this uniform, right? So if b minus a is bigger and you've stretched it out, then the variance is larger because of scale, and it just goes up as you're proportional to how you're stretching it. So the uniforms are fine. They're useful and kind of the basis of a lot of random number generation with different transformations. We'll learn some more about that. But one other distribution we want to look at today is called beta. And the standard beta is a distribution that's between 0 and 1, so it's an alternative to the uniform. Not everything is uniform between 0 and 1. Things are sometimes clustered at small percentages or high percentages or in the middle. Right? And the beta distribution has two parameters. Right? So alpha and beta are both greater than 0. These are parameters. Right? And depending on how they change, it's going to change the shape of the distribution. Right? It's going to make the average higher or lower. It's going to change the variance. It's going to change where between 0 and 1 you're likely to have values. Right? The density for this, so it's for a variable between 0 and 1. The density function is expressed in something called gamma function. And there's an x to the alpha minus 1 and a 1 minus x to the beta minus 1. And so these are certain mathematical functions. There's actually something called a beta function. We're going to not make a huge deal over what these things are defined as, but the gamma function has a, well anyway, they are the things in there that make it so that the integral over the entire space of this f of x dx equal 1. Right? And the gamma functions have, for mostly we'll compute this with densities or just give you the values, but when it turns out to be the gamma of, say, alpha plus 1 has a property, right? That the gamma function is gamma alpha times gamma of alpha. That numerically, well, there's symbols and things that work like that. So if alpha is an integer, the gamma of alpha plus 1 is alpha times gamma of alpha, down to alpha minus 1 times gamma of alpha minus 1. You can take the gamma alpha and reduce it by 1 like this. And if you keep writing it like that, it's going to be alpha factorial. So the gamma function of something like 5 is equivalent to 4 factorial. Right? 1 less, keeping going down. Right? So in this, if alpha and beta are both integers, then this term out front of the beta density is like alpha plus beta minus 1 factorial over alpha minus 1 factorial, beta minus 1 factorial. So it has an effect very much like a combination, right? So in binomial, we had n choose k, and that was n factorial, k factorial, n minus k factorial. This is not exactly like that, but it's kind of a factorial combination thing. It kind of has that same effect of multiplying the, x to p to a power, p to the x minus 1, and then 1 minus p to the power minus 1 in the binomial. And this is similar to that, so it's kind of like a binomial. So it's kind of like a binomial coefficient. Thinking about what that thing is. Yes?
I'm sorry, can you just go back to the last page?
Yeah, so the previous.
Yeah.
The previous one. So this thing is kind of like a combination. And then you get x to a power and 1 minus x to a power. So it's kind of like binomials, like p1 minus p, two different powers. But it's more flexible and continuous.
Okay, thank you.
Yep. So the beta is really, really flexible in terms of how it can show shapes and things. So let's take an example with just alpha equals 3 and beta equals 2. Then this density is gamma of 5 over gamma of 3, gamma of 2, and then there's x to the squiggle, x to the 3 minus 1, and then 1 minus x to the 2 minus 1. So this gamma of 5 is 4 factorial, gamma of 3 is 2 factorial, gamma of 2 is 1 factorial, or just 1. So we have 4 times 3 times 2 times 1 over 2 times 1, so this is 12. So there's a 12 here, and then x squared 1 minus x is the density for values of x between 0 and 1. So you get this function, well, actually a cubic function. So 12 x squared minus 12x cubed. And that's a particular density. Right? If you change these numbers, you get different coefficients, you get different multipliers here, and you get different exponents, right, for things. So, for instance, if alpha is 4 and beta equals 5, then the density, and the number ends up being 280. That's out there. Gamma of 9 over gamma of 4, gamma of 5 is 8 factorial over 3 factorial over 4 factorial. And that number ends up being 280, if you figure it out. And then there's an x to the 4 minus 1 and 1 minus x to the 5 minus 1. So it's 280 x to the x cubed, 1 minus x to the 4th. Right? So that's how these different densities go. What do these things look like? Right? If you get these different ones. Right? Well, we can do that on the computer a little bit. Right? That there is within R a capacity for doing beta distributions. The density function, this d beta, is plotting that function that we've been talking about. Right? So let's take a series of x values going from 0.001 up to 0.999 by sequences of 0.001. Right? So this x, the first 10 values of x are these numbers. And the last ones, the tail of x will give me the last ones are then these decimals, right? So it spans the whole. Right? If we plot x and the d beta at x, we choose its two parameters, alpha and beta. So what was 5 and, was it 4 and 5? Or we'll say 5 and 4 here. Right? And we can make the graph be a nice smooth line. And that's what this beta density looks like. Right? The x to the 4th, 1 minus x cubed, gives a density that looks like this. Right? Do you think the average for this one's bigger than 1/2 or less than 1/2?
Bigger.
Yeah, it's probably going to be a little bit bigger. Right? It's a little bit skewed to the left, but there's more concentration up here above 0.5. Right? If we change those parameters, now if we make it 4 and 5, right, it's a little bit less on average than that. Right? So it's changing the shape. If we get two numbers that are the same, say 6 and 6, is actually symmetric about the middle. If you make one of these, very, like 4 and 50, if you make it very extreme, right, it can be very skewed towards small numbers. Right? So if you're looking at percent of children by county or school district who are not immunized, if you think it's 10 or percent, there'd be some variability by county, but that might be quite small. However, if you phrase it in terms of what percent actually are, that it might go the other way. Right? So 4, and it would be up there. You can get strange things too. Alpha and beta just have to be positive. So if it's 0.2 and 0.2, it could be so that it's pretty extreme, right? Nearly 0, nearly 1 all the time between those two things. And if you get very large numbers, right, they can be very focused in a narrow area. So as you change these parameters, you can get skewness, you can get very focused, you can get very diffuse things, so it can model a lot of different situations. So we want to do a little bit to understand how these things are going on. Right? Let's see what we want to do. So let's try to figure out what the average is. Right? What is the mean of a beta distribution? Where's the average and how does it relate to those two parameters, alpha and beta? So what's the expected value of x? Well, we go back to the basic definition, right? So it's integral where we have density of x times the density of x. So in this case, it's x, and then there's this gamma function of the sum, gamma of alpha, gamma of beta in the denominator, and there's an x to the alpha minus 1, 1 minus x to the beta minus 1 dx. So when you see this, right, what's one thing you would think about doing? Probably combining those terms, right? Dx alpha minus 1. These things actually, and these things as regarding to x are just constant. Those are numbers, like the 280 multipliers. So you could pull those things out. So if we pull those things out, we get gamma alpha plus beta, gamma alpha, gamma beta, and then we have x. Now I could write it as just x to the alpha. I'm not going to write it just as x to the alpha. I'm going to keep the minus 1 there because we're going to look for a pattern. So this integral is actually called a beta integral. It's one of these special integrals in applied mathematics, right? That's the one we're dealing with here. This little part of the density here that involves the x's, sometimes it's called the kernel of the density. So that's where the important action happens in terms of the variable x. This other thing's a constant that helps it all integrate to 1. Sometimes it's called the normalizing constant. Right? But this kernel, again, looks like the kernel of a beta density. So if we had the right multipliers in there, that thing would integrate to 1, right? If we had the right multiplier in here, we would integrate to 1. So we're going to think about adding that multiplier in there. We're going to put a multiplier in here and divide by it out here so that the integral goes away, becomes 1, right? And we're just going to use the fact that this thing integrates to 1 to claim that that works, right? So we have the gamma alpha plus beta, gamma of alpha, gamma of beta. Now what do we have to have for this beta density so that we have the right multiplier out there? So this alpha plus 1 minus 1, 1 minus x to the beta minus 1 dx. So we need our multiplier in there. Maybe I'll put that in blue. we need a gamma term on top up here, and two gamma terms on the bottom. So if we're matching the pattern, right, we had beta here, alpha plus 1, and then alpha plus 1 plus beta on top. So if we had those terms in there, this whole thing, it looks like, you know, that should integrate to 1. Right? Because it looks like this one would be dealing with a new beta distribution. It looks like the density of the beta, alpha plus 1 beta density in there. And it should integrate to 1 over the whole range of x. To make it equal, we have to put this term, the inverse of that out here. Gamma alpha plus 1 plus beta over here. And right, so if that's gone, then we can simplify, try to simplify this thing, right? We're going to use this, that the gamma function steps off by 1, right? So if you gamma alpha plus 1, it's alpha times gamma alpha. So let's write it. Well, these guys, these will cancel. So there's gamma alpha plus beta, and I'm going to write this one in the denominator, gamma alpha plus beta plus 1. And then over here is gamma alpha plus 1. And then over here, gamma of alpha. And so the alpha plus beta plus 1 works as gamma of alpha plus beta times alpha plus beta. And this one, alpha plus 1, is gamma of alpha times gamma of alpha. And so we get some cancellation, and we end up with alpha over alpha plus beta. And this was the expected value of x. So the mean is related to the trade-off between the alpha and beta parameters. So we're kind of seeing that, right? When alpha and beta were, when alpha was bigger, then you know, was 5 versus 4, it was a little bit bigger. When alpha was 4 and beta was 5, it was a little bit lower than 1/2. And so that can change depending on that mix. Right. But any questions? So we're taking as kind of a given that this thing integrates to 1. And once we do that, there is this matter of matching the pattern in here and making it into a density. So that was really kind of the trick to operating on these things. Right, so what's the variance of a beta random variable? So we want the variance of x, which is x minus its mean squared and the expectation of all that, but we can get this thing, squaring that out and distributing terms, we can do it like this. So we want to do expectation of x squared. So this can be kind of the same approach, right? Expectation of x squared, if you write that down as an integral from 0 to 1 of x squared times the density, gamma alpha plus beta, gamma alpha, gamma beta, x to the alpha minus 1, 1 minus x to the beta minus 1 dx. And so we're going to do the same steps. Right? Combine, pull out the constants, put in new constants that make the integral go away as 1, right? And then do some cancellation. It's going to work the same way. So if you follow through some of that stuff, this was our old constant. The new constant, well, I'll write one more step in here. I'll just write the constant that we're going to pull out front. CONST is the constant there. There's an x to the alpha plus 2 minus 1, and then 1 minus x to the beta minus 1 dx. And we're going to put a constant in there to normalize it, and then put the, like before, we're going to put a new constant in here, so that integrates to 1, and we're going to divide by that 1. What you get out of this is you're going to get an alpha plus beta plus 2 in the denominator. You're going to get an alpha plus 2 in the numerator, and the beta is going to be the same that you had before. Kind of going through, if I went through step by step, it would be the same idea, but this is what you would get. So the betas cancel, those things cancel. Alpha plus 2 over alpha, well, you step down by 1. And then there's gamma alpha plus 1, you step down one more time, there's an alpha. And then the rest would cancel. In the denominator, you step down 1, alpha beta plus 1. Then you step down one more time, alpha plus beta. And you would have a gamma alpha plus beta, and that would cancel. So that's the expectation of x squared. The one thing you could check is that if this is clear, can you write out the steps in between to make sure that it's all works out. So the variance of variance of x, then of a beta random variable, then it's going to be alpha plus 1 alpha over alpha plus beta plus 1 times alpha plus beta, minus the mean square, so alpha over alpha plus beta, that thing quantity squared. And if you simplify this thing, there's an alpha plus beta squared in this denominator. There's an alpha plus beta plus 1 from this denominator to equalize it. And then after you cancel everything, it just turns out to be alpha plus beta up here. That ends up being the variance. Yes?
Alpha plus beta or alpha beta?
Just alpha times beta. So that's the formula. One way to think about the formula is, let's write mu equals alpha over alpha plus beta as the mean. What is 1 minus mu? How else can you write that?
1 minus alpha over alpha plus beta.
1 minus alpha over alpha plus beta. Can you simplify that? The 1 is alpha plus beta minus that 1. Put it over a common denominator.
Beta over alpha plus beta.
Yeah, it's beta over alpha plus beta. Right? It's like p, 1 minus p. Right? The means, the x's, in this case, everything between 0 and 1. Right? So this thing, and here we have an alpha over alpha plus beta. We have a beta over alpha plus beta. So this is like the mean times 1 minus the mean over alpha plus beta plus 1. So it's like p times 1 minus p over n. It's kind of like the binomial accuracy, p times 1 minus p over n. So a sample proportion had a variability related to, is it in the middle, or is it all bunched up against one side? Right? And then something like sample size. So the alpha plus beta plus 1 is kind of like a sample size. Right? In the pictures we had, if we got really big versions of these numbers, right, like 200, it's like having a big sample size and a small variance, so it's very tight. If you take that further, to 2,000, right, you're going to be very little deviation from 0.5. But on the other, extreme, 20s, it's more spread out. 2s, right, are really quite, oh, that's kind of interesting picture, right? So that's how that one is, and you very likely can get things. So as sample size gets bigger, as the alpha and beta get bigger in magnitude, right, it becomes more tight, less variance. So let's think about, if you wanted to use this beta as a model for this case that I've been, imagining, right? You might want to think about, where did I write down some numbers? There they are, right? So let's say we look at school districts. Right? And we're going to look at the percent of children in the district who are immunized. And so that can be dx, and we'll report it as a number between 0 and 1. Let's say we think that the mean is 80%, or 4.8, and the standard deviation is about 10%, or 0.1. That would imply that the variance is 0.1 squared, or 0.01. And we wanted to use a beta model to kind of model the percentages, right? So presumably, let's say we can think about what this might look like, right? So the percentages go from 0 to 1, and the mean average is going to be about 0.8. Well, probably if it's clustered up there around 0.8, it's going to be kind of skewed to the right. A standard deviation of 0.1, so kind of most of the probability, plus or minus a couple of standard deviations, maybe a little bit more going low because of the skewness. So our beta density is going to look something like, something like this. Roughly. It's going to be skew, centered up there instead of centered around 1/2. But what are alpha and beta? What alpha and beta match our data pretty well? Right? We have, yes?
Oh, do we set alpha over alpha plus beta equal to 0.8?
Mm-hmm. Yep, that's one part, right? That's one equation. That's the mean. And then if we set the variance equal to this other term, alpha beta over alpha plus beta squared, alpha beta plus 1. All right, we get a second equation, two unknowns, two equations. You can try and solve it. But one way to simplify this, make it look a little bit nicer, right? So alpha over alpha plus beta is this mean, right? So alpha over alpha plus beta is the mean. So there's 0.8
Times 0.2.
times 0.2, because that's beta over that, over alpha plus beta plus 1. And this thing, just to rewrite this, is 0.01. So if you solve these two things, you'll get values of alpha and beta. So I'm going to take this first equation and multiply it by 5. And so this is over alpha plus beta. And so then alpha plus beta times 4 equals alpha. And then, wait, did I do something? Oh, there should be a 5 here. Right? I multiplied both sides by 5 to get rid of this decimal. And then, so beta times 4, subtract the 4 alpha from that side is alpha. So alpha equals beta times 4. Right? So alpha is going to be bigger, right? We need that for the mean to be bigger than 0.5. So if we put that here, so I'm going to multiply by 100. So 16 equals 1. And then there's alpha plus beta plus 1. So 16 equals, well, alpha is 4 beta, and this really is 5 beta plus 1. So 15 equals 5 beta, and beta equals 3. And that means then that alpha is 12. Right? So the beta distribution that would roughly match this situation has alpha equals 12 and beta equals 3. Right, the expected value is to check should be 12. over 12 plus 3, and 12 over 15 is 0.8. Right? If you check the variance, it should work out to be that number too. Right? So what does that distribution look like? We have our plotting ready to go, so check this thing. E beta 5 and 3. Was it 15 and 12 and 3? Right. Right. So that would look like the cumulative distribution, or the probability density function. So what's the chance that a school district has less than 60% of its children immunized? So immunization is supposed to protect the child that's immunized, but if enough children are immunized, there's this called herd immunity. In animal science and things, we call it herd immunity, but the same concept applies to people. So, if 90% are immunized, there's not as much opportunity for a disease to get into the population. So the ones that aren't vaccinated are actually protected by the ones who are. Because if it can't spread, then it dies out, goes away. But maybe 60 or 50% is getting to a low point where there's kind of added risk that it'll be introduced into the population. Right? What's the probability we're less than 0.6? Well, one of these other functions, p beta, under this help, p beta is this, they call it the distribution function. So density is the probability density. The cumulative distribution function, the cumulative, they just call the distribution function. And it's this p, the probability that a beta is less than some number, right? So the probability that a beta is less than x with that line is this picture. So it goes along here almost 0. We start to hit the density, increases, and then it increases to near 1. Right? So if we want the probability, you can put a little line here, a vertical line at say 0.6, and let's make it red. We can make it line width, makes it a little thicker. Right, so here's our line here. What's the probability we're less than 0.6? We can go back and let's put it on that one. Yay, that does that, right? So we're trying to get this little area here, right? If we want the probability. On this plot, it's just this value, right? We just map it over to whatever that is. P, let's just see what that one particular p beta 0.6, one is 12 and 3, here's 0.39. So if we put another line, a horizontal line this time at that value, you can either cut and paste, or you could, and say, let's make that one blue, right? So the probability that we're less than 0.6 under the CDF is over here about 0.04. We can't quite see that from this, but that gives some idea. Right? If you wanted to make that another way, right, you don't have to copy all that number. You could actually put the command right in there, and it will find the value, and you won't see that because it's on the same spot. But in any case, just make it, see, it does change. It's over plotting, so it'll make it purple, right? That it's over top of that other one because it's the same value. In any case, so, but mathematically, how would we find that thing? So we have our density. So if alpha is 12 and beta equals 3, the probability density function is gamma of 15 over gamma of 12 over gamma of 2. Oh, gamma of 15, no, it's 12 and 3, right? Then there's an x to the 12 minus 1, 1 minus x to the 3 minus 1. Gamma 15 is 15, 14, 13 times 12 going all the way down. No, it's not. You have to step down by 1, right? So let me write that, start that again. So this coefficient out here is 14 factorial over 11 factorial over 2 factorial. And it steps down by 1. So there's a 14, 13, 12, and then 11 going all the way down. Right? And in this, there's 11, 10, 9 going all the way down. And then 2 factorials is 2. So most of this part cancels, and we're left with 14 times 13 times 12 over 2. Whatever that is, that's the constant. So it's that constant, and then there's x to the 11th, 1 minus x to squared. 1 minus x, quantity squared. And so to get the probability, get the CDF for this one, right, the probability that x is less than or equal to a value, right, we're going to need to integrate from 0 up to x of that constant of this thing, right, x to the 11th. I'm going to multiply this out. 2x plus x squared dx. And so it's although there's large numbers, it's just a quadratic, it's just a polynomial. Right? Integrals of polynomials are not so hard to do because you just raise it by 1 and divide. And I realize I've kept x and x here, but it's not, I don't think that's a constant number there. So I have my constant number, and then the first one will be just kind of x to 12 over 12. And then there's a minus. The 2x times this becomes x to the 12th, so the power becomes x to the 13th over 13. And x squared times x11 is x13. So you raise that to a power x14 over 14. And that's the cumulative. Right? So the probability that we're less than 60%, right, is plugging 0.6 into that equation. Right? So let's see if we can, we'll make this small, and I'll just kind of go back. So we the constant, 14 times 13 times 12 over 2, is 1,092. And so we need 1,092 times, right, we had x to the 12th over 12. So 0.6 to the 12th over 12 minus, and then we had 2/13, x to the 13th. So 2 times 0.6 to the 13th. And I think I forgot a 12. This would be 12, right? Over 13 plus, and then x to the 14th over 14. X to the 14th, 0.16 to the 14th over 14. So that should be our probability, which matches that p beta. It's in R, just as a side, you can write your own little functions. Right? So this is at 0.6. So say I wanted a particular beta CDF. Beta, this is my beta CDF, so it's not general. Right? But I would give it a number between 0 and 1. And then I want 1,092 times, do a little return here, I'll go with, oops, let me do this. And now I get to type on another line. So 1,092 times x to the 12th divided by 12 minus 2 times x to the 13th divided by 13 plus x to the 14th divided by 14. And I close that off. Now my beta CDF is a function that will evaluate that expression every time I put in a value of x. So my beta CDF of 0.6 is my number. What about 50%? Well, I can put in 50% and then get my number again, or 70%. And so I can evaluate, that's evaluating the CDF for this particular one, right, where I've done it. But in any case, that's the CDF for this thing. So this was about 0.039%. Right? Something else you can do with CDFs, right, is you can find percentiles. So the 100th percentile, right, if P is some number between 0 and 1. So if P is, 75, we'd be interested in the 75th percentile, and things like that. This percentile is the probability that x is less than or equal to its value equals that number P. And so we're going to ask the question, we're interested in a certain percentile, like the percentile for general continuous random variables, it could be just about anything. So if you're dealing with height and weight, what's the 10th percentile, what's the 90th percentile of height and weight by different groups? So what is x that has that percentile? Well, if you have the CDF, the PDF function, you're looking for the value x here that has, P is the area. And you're looking for that x that cuts off that amount. With the CDF, if you already have the CDF function, we can try to approach it a little differently. So if the CDF kind of comes up this way between 0 and 1, and here's the CDF, what we're asking, these were the values of x along this axis. Now we're asking, well, where's the x value that would get us up to a certain percentage on that line? So if here's P, our percentage, where is this down here? What value of x corresponds to that one? So it's doing that inverse mapping, right, once you have the CDF. This thing here is the cumulative distribution function. So it's setting the cumulative distribution function equal to your number P, and then you find x. So let's take a beta, say 3, 2. Choose this one because it's easier to deal with. Right? So the density of gamma of 5 over gamma of 3, gamma of 2, 4 factorial over 2 factorial, 4 times 3 is 12. So this one's 12x squared, 1 minus x, 1 minus x. And so the cumulative, so that's like 12x squared minus 12x cubed. The cumulative distribution function is 12x cubed over 3 minus 12x to the 4th over 4. So that's 4x cubed minus 3x to the 4th. Even this one's a little bit, we'd set that thing equal to some value of P and then solve for x. Let's even make it easier to do first. Let's just do a beta 2 and 1. Right? Then for that one, gamma of 3 over gamma of 2, gamma of 1 is just 2. It's 2 factorial over 1 factorial. So that's just 2. The density of x is 2. Then there's x to the first, right? It's 2 minus 1. And then 1 minus x to the 0. So that's just 2x. So this cumulative distribution, x squared over 2, is just x squared. So what is 100 p percentile? We would p, so x squared equals p. And so the p's percentile for this one is just, x then is just the square root of p. And, right, so. And so it's kind of clumped up near the top. So, so for some of these we can, so for instance, in this case, say we wanted the 64th percentile. For this one, it's going to occur at x about 0.8. Because the square root of 0.64 is 0.8. So if we graph this one, this was a 1, 2, 2, 2, 1. We can look at that picture. Let's graph that picture. The density of this beta, just with 2 and 1, it's just increasing like 2x. Right? It's clumped up near the top. It's more near the top. The cumulative distribution function, p beta, is going up like x squared. The area under that it goes up to 1, and the cumulative, there's a function for that too. The q beta gives you a quantile of a beta. So if we want the 64th percentile of that beta, we put 0.64 there, and it gives us a value of 0.8. It solves it for us. Right, so that's the cumulatives. But in cases like this that are higher order, if we want the 64th percentile of this, right, numerically it's a little harder to do. I don't remember or recall learning all the techniques for solving higher order things past about 2 or 3. Right? And maybe there are. Maybe you're experts at doing those things. If you have access to the computer, it can find those percentiles for you. But another way of thinking about it is that, well, if let's say p equals 0.64, and we're in this beta distribution 3, 2, and we've solved that the cumulative distribution function is this thing, 4x cubed minus 3x to the 4th is the function we're working with. And we're going to set that equal to 0.64, and now we want to solve to find our x value. Again, remember from the picture, as the CDF is increasing, we picked 0.64, and now we want to solve, this is f of x equals 0.64. We're going to try to find that x value to get the percentile. Well, that implies that 4x cubed minus 3x to the 4th minus 0.64 equals 0. This is simple enough, because there's just one dimension to it, that we can get a pretty close approximation by just evaluating that function, the CDF or this other one, at the whole range of values of x. We could divide up this interval into a whole bunch of different points, right? And then evaluate the CDF, 4x cubed minus 3x to the 4th. Right? And then search which values of x give us CDF values that are about 0.64. Right? That'll give us pretty close to the solution, right? A kind of a numerical approximation. So we can do some of that. And we're going to finish up by doing this. So, what was it? So our values of x. So in our environment up here, we have this value of x is 999 values, 0.01 going up, right? So I'm gonna evaluate my CDF. It was 3 times x to the 4th minus 4 times x to the 3rd. Is that right? Or is it the other way around? 4x third minus 3x times x to the 4th. Now I have all these CDF values. I could plot x versus the CDF, so I'll make it a nice line. The line works out nicely because everything's, all the x's are ascending. It was random order, so we get something like that. Right. And now we want the CDF, let's say, do a horizontal line at 0.64. Right. It's about here. So our x value, is that right? 0.64. We thought we were going to get 0.8. So did I do something wrong with this thing? Well, we know this one. It was 0.64 for the other thing, right? We don't know this one yet. The quantile for this beta with at 0.64. Which number are we dealing with? Beta 32. Thank you. 32 is about 0.69. So okay, it looks like we're going to get something close to 0.69. So I could, report the x values where my CDF is, greater than 0.63, and my CDF is less than 0.65, kind of getting in that range. And I get these values. For those values, the CDFs are these values. So here, you have 0.63, these are a little bit small, and then here it crosses over, right, between these two values. So my x value should be somewhere in there, and this one says it's 0.6633771, so somewhere in between those two. You could put a finer grid on there and really get detailed about it, trying to find that point, but this gets it, it's about 0.6, so this is number the 6th and 7th, and 1, 2, 3, 4, 5, 6 and 7, it's somewhere between these two points. And then at least at 3 decimal places is accurate. So anyway, continuous random variable. You get a density function, you can find the CDF. We can integrate to find means or variances. Right. Once you have the CDF, you can get probabilities between things. And we did a little bit of work with the calculus to figure out means and variances for betas and how it's used for a model. So on Tuesday, we'll come back and look at a couple other variations of different variables, do some of the things there, and see how it would match up to different applications. Great, thank you.
I need to relax a little. No, well, I haven't looked yet. No, 52 just was valid and 84 too. Thank you.
Bye, bye.
Yeah.
You know when you're picking housing, how do you know?
Because it just, I think they sent an email, it's just like for 4-person houses.
You're picking market
Yeah.
for 4-person?
That's what we're in, so.
Yeah, I haven't gotten any.
So then, I don't know when the email comes up, if they do like the time,
Oh, but you know it's not gonna be on Monday.
but I know it's gonna be on the day yet.
Oh.
Great, trying to go for it, Alex.
The twos? Yeah.
Two. Hi there, Dan.